Hello, everyone, and welcome to our next seminar of the 7th series of the Latin American webinars on physics. My name is Federico von der Pahlen from the University of Antioquia, and I will be your host today. Our speaker is Luca Visinelli from Stockholm University and Nordita, and he will talk about a very hot subject, a very interesting subject, which is axions in cosmology and astrophysics. Luca received his PhD at the University of Utah, and after postdocs in Bologna at CMCC and at the University of Bologna, he moved to Stockholm, where he is currently a postdoc. So Luca's title is The Axion in Cosmology, and we're really glad to have him today speaking about this subject. I hope there are many people interested in it. And so let me remind you that you can be part of the discussion, writing questions and comments in our YouTube live chat system. So now let me pass you to Luca. Luca, you have to unmute yourself. Sorry.
Thanks for the great introduction and for the possibility to speak today. Okay, so should I start with let's see, how do I share the screen? Here, screen share this part. Okay, good. So now you should be able to see my presentation, right?
Yes, go on. Thank you.
Okay, very good. And I can even put it like this. Okay, so today I'll mainly discuss a paper I've done in collaboration with Sebastian Baum, Javier Redondo, Catherine Fries, and Frank Wilczek. So Sebastian Baum is a graduate student here at Stockholm University. Javier Redondo.
Excuse me, we're not seeing the presentation right now. We're seeing you.
Oh, you got? Huh. Okay. But now, yes. Now you do.
No.
No?
It was for a second there.
Huh.
Just share screen again. Sorry.
Yeah, let me try to unshare. What's going on? Doesn't allow me to share again. What's going on?
Yeah, so let's.
What's happening?
It was working.
So I clicked the green button, right? The second one.
Right.
But now it's not working anymore. Screen share. So strange. So what should we do? Let me try something else.
Yes.
Let me try to join from here. Okay.
Let me see if I can share a screen.
Oh, sorry for that. I don't know what's going on.
Don't worry. Let's see. I'm sharing a screen right now. It's working. Yeah.
Okay, let me try from a different browser. Maybe that's what it is.
But it was working before.
It was working, yes. It was working when we tried, yeah.
Okay. That is the unexpected result of the live streaming, but don't worry, it's okay.
Okay. How about this? Okay. Let's try this. Okay, now it's working.
Perfect. Can you? Yeah, now we can see your slide, but we need you that you close the other browser because now we have you duplicated.
I closed it already.
Okay, so it's perfect, and we can hear you.
Okay, so now it's good. I am screen sharing.
Yes.
Very good. Now what happened? Okay, here, share. Good. Fine. Sorry for the problem. I'll speak quicker. So now it's fine, right?
Yeah, it's perfect.
Very good. So I'll skip the introduction. Basically, I'll talk mainly on the paper that came out in 2018, done in collaboration with people here and with Javier Redondo. You already had the pleasure to host him in your webinar series. My talk will be about mainly about dilute and dense Axion stars, which is the topic of this 2018 paper. I'll take the lead to also talk about other papers that I've done on axions in the past, because I want also to cover the axion as the cold dark matter particle, as a cold dark matter candidate. So in my first slide here, I speak about motivation for the axion. The motivation comes from the fact that in the QCD sector, which theoretically is expected to find to yield a CP violation term. Experimentally, we don't find such a CP violation. So we have this parameter theta bar, which in principle could be of order 1, and then, but in practice is constrained to be less than 10 to the minus 10. So this is a sort of a strong natural naturalness problem. In order to solve for this problem, Peche and Quinn in 1977 introduced a new U1 symmetry, in which this parameter theta is not a parameter anymore, but it's a dynamical field that relaxes toward the minimal energy configuration, which happens to be the configuration in which theta is equal to 0, which leads to a CP conservation from the QCD sector. This is now called as the Peche and Quinn solution, in which there's a new U1 symmetry introduced. Soon after this, in 1978, Wilczek and Weinberg, independently in two PRL papers, realized that an axion, so a new particle, is associated to the breaking of this U1 symmetry. And it's called the axion because it cleans, so gets rid of the Peche-Quinn problem. After this, many models, so benchmark model like the DFSZ and the KSVZ model were introduced. In the DFSZ model, we have additional Higgs fields, while in the KSVZ model, we have an additional heavy quark. So these are sort of minimal models that augment the standard model and also include the axion. So they're sort of minimal viable axion model and are still the benchmark model today. So these are the models that people test and look for axions in today's research. The same year, so early 1980s, the axion was also pointed out as a possible candidate for the cold dark matter. And this is why the axion is such an interesting particle for its phenomenology, because it could both solve the strong CP problem within the QCD sector of the standard model and provide a solution of the dark matter for the dark matter problem. All of this within basically 2 orders of magnitude spanned by the possible values of the axion mass. So it's a sort of well-constrained problem that people are now trying to address experimentally, as I'll talk in my slides later. So, axion coherent oscillation. The axion is a very light particle with its mass in the range of the 10 to 100 of microelectron volt, if we want to address the axion to be the cold dark matter. And to do so, in order to be a cold particle, it has to be produced non-thermally. And a way to produce it non-thermally is through this misalignment mechanism in which the Axion sits at the bottom of a Mexican hat potential. This is through the usual Pechequin breaking. But then, at temperatures that range at the order of the QCD phase transition temperature, non-trivial QCD effect tilt this Mexican hat and the Axion, which could sit anywhere from 0 to pi, and at the bottom of this potential, feel the presence of this additional potential, of this additional tilting, and start to roll towards the true minimum of the potential. So where to the minimum of the potential with a coherent motion. And this coherent motion today behaves as cold dark matter, as we see in the next slide here. This is a slide from Javier, in which the Axion could sit anywhere between -pi and pi. It starts to roll down. And if you take into consideration the equation of motion and you solve it, you actually find that in any cosmology, so for any given value of any given time dependence of the Hubble rate, your energy density of Axions always behave as a cold component, so as matter. So it scales as the scale factor to the -3. This is today's perspective and the future searches for Axions in the laboratory. So on the x-axis, I've put the Axion, the mass of the Axion in electron volt, ranging from order 1, 10 electron volt to 10 to the -14. And on the y-axis, I've put the Axion photon coupling in the inverse GV. So the solid regions are regions where the searches has already been excluded, except for the yellow band, which corresponds to viable Axion models, the DFSZ and KSVZ models I've discussed previously. The hashed regions are future regions that would be in reach of given future experiments that are either underway, like IAXO, or proposed, like Abracadabra. So the Axion acquires an effective Axion photon coupling through a fermion loop, and this is the inset diagram that I've put on this slide. If you compute the value of G through Feynman diagrams computation, you actually find that G is proportional to the Axion mass. This is why the line, the KSVZ and the FSZ lines, are lines with a constant positive slope, because G is proportional to M given some theory. So you choose your theory. So you choose basically the charges that are at the vertex of this Feynman diagram, and you gauge where this proportionality constant is, where this line is. Okay, so we see that there's a lot of parameter space still to cover. The CDM, okay, so this yellow band here is divided into various different regions. I've put the CDM bound here in light red. This is the region which corresponds to around 10 to the -5 electron volt in Axion mass. This is the region in which the Axion is favored to be the cold dark matter particle. So if the Axion has a mass and a coupling constant, so that it lies in this region here, it would solve the cold dark matter problem. If the Axion is heavier, it would fall into the subdominant part here. So it would still be a particle, a proper particle that exists in the standard model and solves the strong CV problem, but it would not lead to a solution of the the cold dark matter. It would be a cold component of the universe, but it would be a subdominant component. The excluded region comes from the fact that if we go in this region here, the coupling constant would become too strong, and we would have astrophysical effects like cooling of white dwarfs, or we would have seen effects coming from the 1987 supernova. Okay, all of these regions that I've talked about now assume that the initial value of the Axion field, so where the Axion field sits at the beginning of its evolution, is of the order of 1. But the Axion field initially can be much lower, can have a lower value, have a lower value of order 10 to the minus 1 or 10 to the minus 2. So we can fine-tune this parameter in order to have the proper amount of dark matter today. And this is what's called the anthropic region. So basically, going lower in mass from 10 to the minus 5 down to 10 to the minus 13, 12, roughly, the Axon can still be the dark matter, but the initial value of the misalignment angle has to be fine-tuned in order to fulfill this requirement. Otherwise, if we start with a value of theta of the Axon angle that's of order 1, so that's too large, we would have too much dark matter today. We would overclose the universe, and this would not be allowed, of course, would be against the data that we see. LIGO here is the proposed detection by Arvanitaki, and the Planck region here means simply that F will become trans-Planckian here in this region. So I just excluded it. Okay, anywhere else in this parameter space, so away from this yellow band, away from the QCD Axon band, we would still have particles. It's possible that we find axions in these other regions, but these would not be the QCD axions in the sense that it would not address the strong CV problem. It could be dark matter particles, but they would not be the standard model axion, the axion that solves the strong CP problem. They're called ALPS, axion-like particles, because they share similar properties to the axion. For example, the same effective axion photon coupling, and there would be pseudoscalar bosons basically arising in various theories. Okay, today a new PRL paper came out, and okay, what's going on? Sorry. Oh, okay. New PRL paper came out, which is this solid dark blue line here that extends the previous finding of ADMX to a region in which the DFSZ axon is also probed. So this is basically an expanded region that shows this results better. So basically, going back to the previous slide, comparing here with the previous result of ADMX here, which could barely touch the KSVZ line, the new result extends to the FSZ in a portion of the region that was probed before. So this is a very narrow band, but the ADMX work takes actually a lot of time every time they have to recalibrate the whole experiment, the whole set. So if they knew where the axion were sitting, they would be very fast in finding it. But since we don't know, even in principle, what the axion mass would be, could be anywhere in this micro electron volt to hundreds of micro electron volt range. they have to reset every time the cavity. Okay. Now, this is again from Javier. So what happens here? This is a numerical simulation in which the Axon field, actually the whole Pechet-Quinn field, so the whole complex field is simulated, in which the Axion is just the angle variable of a complex field. In this scenario here, the Pechet-Quinn breaks after inflation. So we don't enjoy the benefits of inflation, which basically erase all of the substructures and leaves us with a smooth field. But we have to deal with all of these field structure, in which the Axion field ranges from minus pi to pi, and the Axion energy density varies within the same Hubble patch. This leads to various different features today that are actually detectable. One being the Axion string network. So there are regions in this 2D slice in which the Axion field winds up from minus pi to pi around a point. And in 3D, this point is actually a line in which the Axion field winds up around. This is called an Axion string. So, and it's to a high degree of to a high degree of precision, this is a cosmic string. Behaves as a cosmic string. So for that reason, you want to get rid of that. You want Axion strings and other topological defects like the walls that are in this other picture here to wash out. Otherwise, we would see their effect. They would come to dominate the universe today. And there are actually debates on how this Axion string condensate decays into axions. So these are additional sources to the cold dark matter component of axions today, because they would also radiate and decay into cold axions. And the effect could be of the same order, if not more, than what we find from the misalignment mechanism. Okay. Another effect would be the Axion mini cluster. So in some regions, the overdensity would actually be of order 1, if not larger. I think here in this paper by Kolb and Kachev, who were the first among the first ones to study this effect, the overdensity goes to be of order 20. So these overdensities in the Axion energy density detach from the detach and basically freeze out at the matter radiation equality. They would form structures that are basically would lead to some effects, to some power spectrum erasing, which could be could have some imprints today, and I'll talk about this in a slide later. If the Pechet-Quinn breaks during or before inflation, we have the breaking, so we have all of this field with different configurations, but inflation singles out a patch in which theta is homogenized. So we don't have any of these features. We don't have mini clusters. We don't have strings and walls because they have been washed out. They've been taken far out from the Hubble size by inflation today, and we just have to deal with one initial configuration. So what's the amount of dark matter today? What is the allowed parameter space? Since inflation plays a role here, because whether the Pechet-Quinn symmetry is broken before or after inflation, we have two completely different scenarios. We also have to take into account when inflation ends. And this is the Hubble rate at the end of inflation. It's a new parameter in the theory. This is taken into account here. So in this slide, in this plot, I've put the HI, the Hubble rate at the end of inflation, on the x-axis. This in single mode inflation is directly related to R, which is the tensor to scalar ratio, which is a measurement of the primordial gravitational waves, basically the amount of primordial gravitational waves spectrum. On the y-axis, I've put on the left the Axion decay constant, which ranges from 10 to the 9 to 10 to the 18 GeV, roughly, when the Axion decay constant is inversely proportional to the Axion mass, which is on the right-hand side of the y-axis. And we see that the Axion mass is of the order of the micro to, well, milli, micro, nano electron volt. Okay, so these are the energy scales that are in play here for the Axion mass. I've put some of the known bounds. So for M, I've already talked about the upper bound on the Axion mass, which is there here with the red giant brightness, but there are actually various astrophysical constraints that come from either red giant brightness or wide dwarf cooling time. It depends on the Axion model you're dealing with, whether if DFSZ or KSVZ, but they point at around the same order of magnitude for the bound on the Axion mass. As for HI, tensor mode constraint R to be smaller than 0.07, and there are actually forecasts for the next generations that would push this value to being below 10 to the minus 10 to the minus 2 or even 10 to the minus 3. This is the forecast that I've put here without coloring in yellow. Okay, so this is the ADMX with its forecast result. This is the result that we already knew of ADMX. The forecast is for the future experiment. So when the ADMX will be over, this is what they want to have covered. This is the proposed MADMAX and the proposed IAXO forecast. So some regions of the parameter space here will be probed in the next 10 years, 5 to 10 years. Okay. Okay. This line here, FA equal to HI, separates the two regions between the two scenarios that I talked before. So the scenario in which the Axion field breaks, the Pechequin symmetry breaks during inflation, and this is the scenario on the top left side, from the scenario in which the Axion field breaks after inflation. This is the bottom right side. So basically, high value of FA correspond to breaking during inflation. Lower value of FA correspond to breaking after inflation, roughly. This is because isocurvature fluctuations are produced during inflation. So the Axion would both have isocurvature and adiabatic fluctuations during the spirit, and the isocurvature fluctuations are constrained by Planck. So we see that we cut out a huge region of the parameter space, but we're left with a window here, which nevertheless hints at a value of R which is really low. So in order to have anthropic axions, so axions for which the initial value of the misalignment angle is small, 10 to the minus 2 to 10 to the minus 3, in order to have the correct dark matter abundance, we need R to be less than 10 to the minus 9, 10 to the minus 10. So of course this is even a theoretical challenge, because R can be, well, there are many sources of primordial gravitational waves that could hint at R being of the order 10 to the minus 3. We will know soon, but soon in the next 10 years, but would be really problematic to have an axion in this window. Let's turn our interest to the other end, so to the other scenario, in which the axion is produced after inflation. So omega A larger than omega CDM is the bound for the overclosure. So you don't want to produce too many cold dark matter axions. And this sets a limit from below on the axion mass. The parameter alpha here parameterize the amount of axions that come from strings, from topological defects, to those that come from the misalignment angle. So alpha equal to 1 means that have the same contribution from these two effects, to alpha to 100, meaning that we have 100 more times axion from strings and other topological defects other than the misalignment mechanism. So the alpha equal to 1 or alpha equal to 100. So there's been a huge debate in the literature of what's the value of alpha. This actually is not quite settled. So semi-analytically, there were two different sets of paper debating about whether alpha equal to 1 or alpha equal to 100, 200 even. Numerical solutions of the string condensate hinted at alpha equal to 10, although more recent results hinted alpha equal to 1 even for a numerical solution. So this is not settled yet. And there is a lot to say. Now, I want to talk more about mini clusters and dense and dilute stars. So mini clusters are over 1 over densities on the initial spectrum of axions. So the mass is the mass enclosed within a Hubble rate when the axion fields start to oscillate, which correspond around to the QCD phase transition. While the radius is fixed by the density given at the matter addition equality. These are the computations that I've done for an axion mass of 100 microelectron volt. So this is for a sizable contribution from axion strings. The mass is of the order of 10 to the minus 16 solar masses for a mini cluster, but you can go and have axion mini clusters that are up to 10 to the minus 12, minus 11 solar masses. It's easy to tweak these models here. And the radius is of order the astronomic radius, so the Earth to Sun distance. So the problem with the mini clusters is if most of the axions are in mini clusters, and we don't know what, today we don't know what the fraction of axion actually condense into mini clusters. We would have very few encounter with these objects. So we have like one encounter every million year of 100,000 years. So it would be very rare. And if most of the axions are in these structures, this could affect the direct detection of axions. Or even if axion mini clusters axions are not mostly condensed into these structures, still we would have to take into considerations this structure in any case, even if we find the axion to be the cold dark matter, because at that time then we would need more precise and refined measurement coming from the density distribution, from the energy density of the axion, and this would in any case have an impact. So we have to take out the fraction of axion that goes into mini clusters if we want to make a precise physical estimation of the cosmology of the axion, if this particle is ever found and it is the dark matter. Now, what are the axion stars? So this is another piece of history that's currently missing and requires further a lot of studies. This is what I think. So axion stars are boson stars, where the boson is the Axion. So the boson stars have been known since the late 60s. So these are well-studied objects in which the self-gravity, which is the first term in this U, in this potential energy, is counterbalanced by the kinetic pressure, which is the second term, m square v square, m half v square. So for Axion stars, the kinetic pressure is provided by the fact that you are packing a coherently oscillating field into an object of a size r, which means that it's the Heisenberg uncertainty principle that gives you the required motion of the particles, the uncertainty momentum spread, which gives the kinetic pressure. In addition to this, we have added a third term, U self, which is the Axion self interaction. So not only the quartic potential, but the whole cosine potential that the Axion feels when the Mexican hat potential tilts. So we have added all of these terms in our analysis in the paper. So for the paper that we have cooked up, we do not talk about the formation of these objects in a cosmological environment or astrophysical environment. We just talk about how Axion stars would look like today, because that was a missing piece, and there was some literature we were not actually satisfied with, and we were criticizing in our paper. The formation of Axion stars is a completely different topic, and today there is still a lot of work to do. We think that Axion star could form cosmologically inside the Axion mini clusters. So if you are able to produce a numerical simulation that's refined enough to look at the mini cluster and look inside of it, you should be able to distinguish the Axion star. Or they could, this is what has been done in 2014 with ultralight Axion that self-interact. This object could also be formed hierarchically. Okay, but this is not what we covered in the paper. We only covered the hydrostatic equilibrium, which is given by this plot here. So on the x-axis, I've put the mass of the Axion star in these fancy units, which is f square over m. We use these units because they're so universal profile. That's not only good for the QCD Axion, but also for Axion-like particles. This isn't against on the y-axis the radius of this particle of this object in units of 1 over the Axion mass. Okay, so let's start from the top. Okay, so this line here, the negative slope line, represent the first two pieces. So we just neglect the self-interaction of the Axion, and we look at the hydrostatic equilibrium of the objects in which the kinetic pressure is counterbalanced by gravity. So for this branch here, which we call dilute branch in the paper, the self-interaction is actually negligible. So if you put yourself into this region of the parameter space, the self-interaction can be safely neglected. These are stable configurations in the sense that the second derivative of the potential is positive, which also means that if you displace a little stable configuration from this blue line, it would return, dynamics would be such that the Axion star would return to this configuration. So these are viable Axion star configuration today. They would survive to today if they're not stripped away by tidal disruption, or if they survive further mechanisms. What happens next? So what happens if you increase the density. So if you increase the density, you move along this line, and this is given by these arrows here. If you increase the density, you basically arrive at the point in which the self-interaction can no longer be neglected and actually overcomes the effects of the self-gravity. So you have to remember that both self-gravity and self-interactions are attractive. That's why they can counterbalance the effect of the kinetic pressure, which is repulsive. Okay, so if you do the computation, you find that the radius is proportional to the mass. That's why the slope now is positive, but the second derivative is negative, which means that these the Axon stars here in this configuration cannot be existing. They either blow up and go back to the dilute configuration, or they collapse to what? Well, black holes, maybe. This other branch that's below, maybe. Let's see what happens. What's important to see is that there is a kink here between the dilute and this red slope branch, and you cannot find any Axion star that has a mass larger than the critical value that's given at this kink here. So this is a sort of cutoff value, which for the QCD Axion is of the order of 10 to the minus 12 solar masses, above which Axion stars in the simplest configuration don't exist. Now, if you keep increasing the density of your Axion star, so if you keep cramming axions into these Axion stars, you actually end up to a configuration where you reach basically the value of the Axon field to be of order 1. In this region here, what we criticized in the previous literature is that they would still use a non-relativistic approximation, but now axions in this configuration are relativistic. So you have to use the whole Klein-Gordon equation, actually the sine-Gordon equation, if you use a sine potential for describing the self-interaction. What we found numerically is that the density is constant, which explains why we find a relation between the radius and the mass, as given here, are proportional to the mass to the 1/3, because this would yield a constant density. But the important thing is that these objects are metastable. So an Axion star in this configuration would radiate away relativistic axion, shrink until it goes back to the kink, and then collapse, which means that these objects also don't exist. This was the original motivation of the work. I was reading about these dense Axion stars, and I was checking if they could also give a signal in gravitational waves, like from spiraling, merging, or other types of signal. But while redoing the computation, I found some discrepancies, and this is the outcome of that. Actually, the whole picture, what the Axion stars do, is the outcome of this curiosity. But there is a lot more to do. There's the whole picture, the whole history has to be defined. People still don't know, because the numerical simulations start to be available and accessible now. This is basically what I want to do in the following months and years. Okay, so I've come to the conclusion, which basically I hope I showed you that Axon actually are well motivated. It's nice to know that they are also falsifiable, because there's just a couple of order of magnitude in which the QCD Axon could live. It could take decades, but still we would get there at a certain point. we need a lot of work on understanding mini cluster and axion stars from first principle, and to actually be able to give a number for the fractional actions that today is condensed into streams and mini clusters. That's all. Okay, thank you.
Okay, thank you very much for this very interesting talk about the Axion landscape and prospects of understanding the structure of axions. Now, let me remind you before we pass to the questions that you can take part of the discussion writing questions and comments on our YouTube live chat system. Okay. So first, I will pass you to the questions in the audience, if there are some. Yes.
Yes, I have a question for Luca. First of all, very nice your talk, Luca. I was very, I got my attention about these action stars that you were talking at the end. So one question would be, do you expect that this action stars radiate photons? Let's say, because at the end action decays into 2 photons, let's say when they are in vacuum where not this overdensity. But do you expect that these are could be mistaken like a regular stars, or just like a star that emit monochromatic photons, or monochromatic plus some dispersion because some extra effects or something like that?
Okay. If it's just axion star, I would not, because well, think of the Feynman diagram. That's an axion that goes into 2 photons. So you would need a. So what can you have? You can have an axion decay into photons, and that basically is. We know that for the QCD axion, this is too long. It's many orders of magnitudes larger than the age of the universe, and the frequency of the axion of the photon that would come out would be a fraction of a milli electron volt. So would be very hard to detect, if ever. So for the axion star per se, I would say no. But we don't know what's the distribution of these axion stars and also mini clusters, because the mini clusters are the objects that are actually out there. The axion stars are just the cores. So what would happen? What if these objects encounter a magnetic field? Then things would become interesting, because then you would have a conversion of these actions, like some emission. It would be eaten up by this magnetic field, probably. This is. I don't think this has been done, but. Much. So this could happen, definitely. Yeah. For the signal, you would first need to identify where this region of a large magnetic field is. Of course, I'm thinking of a neutron star now, but the cross section would be too small, right? The cross section between a neutron star and axion star would be too small, or even a mini cluster would be too small to give a probability for this encounter, I think. So you need first to find a galactic environment and then make computation of this, I would think. But in that case, it would be possible.
So, but kind of continue with the question, because I was curious about these action stars. But like an star made only of action could be kind of rare, let's say, for the stuff that you were saying. But wouldn't be an extra signal if these action stars are surrounded by baryons, and kind of there is an interplay between a small component of baryons in these action stars, so you have like a, I don't know.
Oh,
without a neutron star,
like I call them stars because I call them stars because of the hydrostatic equilibrium, not because they shine. Yes, this is maybe that was the first thing to say. So the stars in the sense that you have a balance between the self-gravity and the kinetic pressure. There was a study on the accretion of matter like hydrogen from these objects from the dense branch, but they were using the previous results in which these dense stars were stable. And dense stars are not stable because the axion is relativistic inside of them. So you have to basically today the second and third branch don't exist. You only have axions in which the gravity and the kinetic pressure are counterbalanced, and these are boring because they're not dense enough to produce any too puffy to produce any interesting effect in the sense of gravitational waves or in the sense of accreting material. They could be interesting for other reasons, like when they get stripped or if the Earth goes through them, but not for these other effects that you're asking, like for accreting material.
Mm-hmm. Okay, thank you. So I don't know if there are other questions for other people.
Mm-hmm.
No, yeah, that was my question about the stability of the.
The stability.
Yeah,
yeah,
that was my question. Yeah,
yeah.
So
Only the first branch is stable.
I see. Thank you.
So the third branch would be stable in the classical sense, like if you do the classical stability analysis, but you have the relativistic effect and the quantum effect also that come in. The quantum effect being this release of axion or of relativistic axions.
Okay. Yeah. Thank you, Luca.
Just like a question from someone who is ignorant on this subject. I didn't really catch up. What's the largest structures that these stars can have, of these creations can have? And I was wondering if that could have any effect on dwarf galaxies, but I guess you answered that they don't.
Well, you have to remember that these are dark matter candidates. The Axion is a dark matter candidate. If they clump into mini clusters, if most of them clump into mini clusters, then the mini clusters become the building block. It's like having particles. It's like having the Wimzillas, basically. You don't have a coherent field of axions anymore. You have these objects that then undergo hierarchical structure formation. So first you form the mini clusters, and then at the time of structure formation, you form halos of mini clusters. Yeah. So the thing is that the mini clusters are much smaller than the free streaming length of that you would find with WIMPs. So you find a structure formation that's different from what you expect from with WIMP dark matter. This is another aspect that has not been really covered and that I really want to address in the near future as well. Like, so there are some papers on structure formation with axions, but there's still a lot more to do, especially in view of the new numerical simulations that you can perform with the Pesequin field.
Okay.
For the size, yeah, it depends on the axion model, on the model of the axion and on the mass. What I said before is 1 AU, astronomical unit. That's for the most interesting case, for the QCD axion and for the QCD axion that is the dark matter. But you can think of ultra-light axions. You have basically two parameters to to tweak the value of the axion mass and the decay constant, which for an axion-like particle are not related. For a QCD axion, they are, but for the axion-like particle, not. So, yeah.
Okay, thank you. Are there more questions? I don't see any questions on YouTube. So last chance. Well, if not, let's thank the speaker again. We learned a lot, at least I did. And we'll see each other in our next webinar in a few weeks. And so, thanks again.
Thanks.
Thank you very much. Bye-bye, everybody.
Bye.